Hello, today I'd like to show you a post-processing in ParaView. So the first thing we're going to do is we start ParaView, and in order to do post-processing of NACS result files, we have to check whether the NACS reader plugin is installed. Therefore, we go to the Tools menu, click the Manage Plugins item. Here, no NACS plugin is registered, so we press Load New. And on Windows operating systems, we can find the plugin in the bin directory. In Linux versions of ParaView, it can be found in there, or it should be placed in the lib subfolder. So we go to the bin folder, and there is a NACS reader DLL. We select that, it's loaded, and if it should be loaded per default for future calls of ParaView, we can press the autoload checkbox right here. Okay, so first step is to load a NACS result file. Therefore, I navigate to a certain folder and load a NACS result file. So on the lower hand side, you can see the dialog window of our NACS reader. You can select certain NACS regions that you want to see. You can also enable certain element groups or node groups. This is relevant for harmonic or modal analysis. So in case that you want to visualize certain harmonic mode shapes or vibration mode shape of modal results, you can click right here, and then you can select which steps you want to see and then animate that vibration mode shape. You can select whether you want to see complex results with amplitude and phase or with real and imaginary part. So we just press apply at that point. Then it takes some moments and we can see our simulation model. Here on the information pane, we could also see what's contained in our dataset currently. Several blocks with the region names are available, and some results like the acoustic pressure, the node numbers, and the mechanical displacement. So what we're gonna do now at first is we're gonna separate acoustic domains from mechanical domains using the ExtractBlock filter. So that filter can either be found by pressing filters, alphabetical, E like ExtractBlock, and if we want to do that, then we can select which regions we want to obtain right here. So at first we select the air as the only acoustic region, and we could also rename that filter something like called maybe acoustic. Then we select once again our NACS reader element, and we could also press to add the ExtractBlock filter Control and space. Then that dialog window appears and we just type ExtractBlock and there it appears. Press enter and then we added that filter again. And this time we want to add all mechanical regions. So these are all regions without the air. So we've got two things. We've got, maybe we rename that block also and call it mechanical. Then we could do something like switch off all acoustic regions. Those are the domains that go to the mechanics, and those are the domains that we want to visualize for the acoustic results. Let's start with mechanics. So here's something like the mechanical displacement is available as result. What we see here is the first analysis time step. Not too much happens here. There's a very useful toolbar. You can enable it using the View menu, and then there is something called Animation View. So right now here several time steps are depicted, and we can just pull that slider here to a certain time step and see that something will change. So here we can see the current active mechanical displacement magnitude, and it's in that value range, and we can see that the results we see in that time step are much higher than what the color bar currently allows us to see, and therefore here is a toolbar, the results toolbar, and here's a rescale to Datarange icon. We just press that, and then everything it rescales to the maximum of the mechanical displacement amplitude. Something very useful typically for visualizing the vibration is the WarpByVector filter. So we select our mechanical item and then use from that main filter toolbar the WarpByVector icon. Then a new filter is added, and here the quantity that should be used for the warping will be selected. In that case, it's the mechanical displacement, and here we can see that our vibration amplitudes are not that high, so just 40 nanometers. Our dimensions can also be visualized, for example here, if I go to the lower pane, there's something called cube axis visibility, and that allows us to see the dimensions of our model. And here we can easily see that we are in millimeters, so those are something like 25 millimeters, 50 millimeters in length, and these are 20 millimeters in width. So right now we can see that this is a very thin plate, so the warp scale factor, if we want to arrive at, let's say, millimeters, should be something like 1 to the power of 5. Yeah, here we can already see something. Maybe it's already a little high. Maybe it should be better to see something like that. So this is how to use that WarpByVector filter. Now we can see that maybe in that color bar has a certain preset color range, and if we dislike that, here in the results menu you've got that edit color map icon. If you click on that, the right dialog that you can see right here opens up, and here we can select another preset. For example, something like a typical blue to red, rainbow or jet color scale. So we press apply, and we can close that. Everything is recolored, and if we think that this should be the default for all future color bars, then here we have got that save current color map setting values as default for all arrays. We click on that, and right now for all future quantities that we want to visualize, the same preset will be chosen. So this is concerning the acoustics. What we also want to visualize is, of course, for the mechanics, what we also want to visualize is the acoustical domain. This is depicted here, and here we can see the acoustic pressure. So this is the acoustic pressure that we can see. Maybe we want to resize this also, but this is already the valid range at that time step. Typically we don't use something like directly the acoustic pressure, but maybe something like the sound pressure level, which is a little hard to compute in the time domain, but we can try something like that. We use the calculator filter, attach it to that acoustic ExtractBlock filter. Here in the calculator we can specify which name our resulting quantity should have after that computation, and we just call it SPL, like sound pressure level. And now we have to type the formula. That formula for computing the sound pressure level is 20 times the logarithm to base 10 of the acoustic pressure divided by 20 micropascal. So this is what we type in here, 20 times logarithm with base 10 of acoustic pressure divided by 2e minus 5. So this is what we obtain. We could also do something like the following to make it even clear what we do. Of course, our acoustic pressure has also negative values, so it's more reasonable to type something like the absolute value of the acoustic pressure divided by 2 to the power of e minus 5. So this is what we obtain as a result, and we can see right here that between 100 and minus 100 dB, which is the unit of that result quantity, is our current acoustic range. This is maybe a little too high. If you want to see something even better, we can change the limits by clicking on that rescale button with a C on it, like custom range. So let's say we want to use a range of something like 60 dB, so minimum would be 40 dB, maximum is 100 dB, so it looks just like that. You can see whether something changes still. Okay. So other things which might be interesting for you are, for example, something like the clip filter. The clip filter allows to cut the computation region. You can try that right here. We attach to our calculator, which we could also rename to something like to SPL dB. And right now we attach that clip filter. So we can see right here a clip, a clipping plane is visualized. Here we got that handle that allows us to rotate the plane in a way that we want to have it maybe. And if we're not sure what we want to do, we can also reset it again and can try to do it either with an X normal, Y normal or Z normal. So we take the X normal, press apply, and so at first the data range has been resetted. This is maybe a bug in the ParaView 4.4 version, but we can easily put it to the old limits again, and then the result looks like that. So here this is where we started, this is where we end up. So we can directly see what happens right here inside the field of interest. So another thing which might be useful right now is, stepping back to that, we want to maybe visualize the vibration of this media in between. And therefore we can again attach to that mechanical ExtractBlock filter another ExtractBlock filter that allows us, for example, to just select the paper, and if we want to rescale right here, we can see that we can also attach another WarpByVector filter to that domain, and here we can use a scale factor 1e to the power of 6, maybe a little larger. Okay, here we can see something. Here the vibration amplitude is getting higher, so we can again rescale it maybe. And we can see what happens by pressing the play button in that animation control. So you can easily see, so rotate your view, what happens. Here we can go back to the start. Here we can start the animation, so we see what happens. Well, we don't see too much currently, so one thing that would be interesting is still at which time are we currently. Therefore we go to the filters menu, go to temporal, annotate time filter. So here we can choose how to display the time. Here is time, the format that we're using as floating point number either. So we could write something like we want to have 1 decimal after the comma, and maybe we want to show that in microseconds. Therefore we have to scale our time values that you can see here on top. So this is 2 to the power of minus 6 to microseconds, and if we do it like that, we can see here on the bottom our time. we can also tell ParaView where to place it. Either you use that lower left corner offset value, so something like that, to modify the position. You can freely choose where to put it, or you say, well, use a window location here in the middle center of the bottom middle center. The time should be presented. And you can also adapt the font size, but that should be printed in bold, italic, something like that. Okay, so these are the first steps that we want to do. Let's see what happens. So now we at least see something, but what is the cause of that wave that is launched here? As we could already see right here, we also have the acoustic domain, and another very popular thing to visualize is the contour, the ISO contour levels of the acoustic wave. So we choose that contour filter. We want to use the sound pressure level, that is depicted right here as contour levels, and here we want to tell him which level is interesting for us. And we say, well, let's try something like 65 dB. When we are finished, we press apply. So currently we cannot see something because we are at the very beginning, but here we can already see that an acoustic wave is also visible right now. So that acoustic wave can be colorized, but somehow here our sound pressure level doesn't appear anymore. This is due to the fact that here the compute scalars checkbox hasn't been enabled. If we enable it and press apply again, the result will appear. And so we can easily see what happens here on top. An acoustic wave is launched, and we see here the deformed geometry, and here also the wave that is traveling to the bounds of the acoustic domain. We might also be interested maybe seeing where that wave was launched, and therefore we will go again back to the mechanical extract block filter, and we'll use another extract block filter, and here we want to see our piezoelectric devices, and we will not colorize the displacement range, we will just plot them as with the VTK block index, so we can just see that there is something. Now our data range has been changed, but here we can easily show the original range again. So what we can see currently is that a wave is traveling from the transducer to the paper, and that wave is then launching an acoustic pulse on the other side as well, but this pulse is not visible. Why that? This is due to the double impedance shift, air to paper, paper to air. That means we maybe need another contour level. Therefore I could either enter right here another contour levels, like something, let's say 35 dB. And so we can also see the acoustic ISO surfaces on the bottom side. Maybe right here we could also change the values that we want to visualize to, let's say, something like 30 dB to 80 dB. Okay, so we can see what happens down here. Here we can still see another item. This is the extract block, the VTK block color, and this stems from the extract block that we did down here. Here we can just deactivate the visibility of the legend, and so we should be slowly able to see what happens in this simulation. So here a wave is launched, then it's traveling to the lower domain, and here of course also a vibration is initiated. If you say, well, now I can't see anything concerning the paper vibration anymore, well, if this is a problem, then We could also apply a clipping filter right here, and we did that already, but the contour filter is living still on that dB. So if we want to use the clipped dataset as source for our contour, for our isosurfaces, we right-click on that isosurface filter, the contour filter. We want to say that we want to change the input, and our new input will be the clipping filter. If we do that, then we can see that right now our isosurfaces are only visible on the back side. If that frame is something we don't want to see, we can deactivate that frame by unchecking the Show Plane checkbox of the clipping filter. So this is what we did, and if I want to return right now to the very beginning and say start, then we can see what happens. Here the acoustic wave is traveling. Here the vibration of the paper can be seen, and here on the lower side also some waves are traveling and finally arriving at the piezoelectric device. So at that point, this is everything I wanted to show in this tutorial concerning the use of ParaView for vibroacoustic simulations. Once that you've set up all of that pipeline, maybe you still want to save what you have been doing, and therefore you go to File, Save State, go to the directory where your result file is located, and then you can save your result file, maybe call it paper thickness sensor ParaView, and then here we press return. So we saved this as ParaView state file. We can also save it as in the same dialog, save state as right here Python state file. So if we do that, it's saved as Python state file, and here in the save dialog we can say what we want to save in the Python objects, just the modifications or all properties of the Python objects. We save just the modifications, so we are finally finished. If we're interested in exporting a picture, for example, we can do that by saving a screenshot, for example. Right here, here's a checkbox, save only selected view. If we would have more views, we could select which view to use. Another thing that we can do is right here, File, Save Animation, and therefore an animation of all of those files will be saved. We have 200 time steps with a frame rate of 15 frames per second. That should be something like 7 seconds. So we could try how much time that consumes. Here we can choose our data format that we want to choose, either an OGVorbis file or an AVI file or image files. Then all single frames will be exported as images. We select AVI, press the file name, let's say paper thickness 3D.avi, press OK. And you can see that now this animation is at first shown on screen, since it's rendered at the screen, and then it will also be available as a result file, as AVI file in the end. At the lower pane you can easily see the process of the generation of that AVI, and I think in a few seconds this movie file should be ready. So we could start to navigate to the folder where we want to store that animation, and then we can review the result maybe in the Windows Media Player. So here the file is generated. It still takes some time until we get there, 80%, and I think in a few seconds everything should be done. So of course, if you want to replay that state file that you've been saving, you can automatically exchange your NACS result file, so this process will be saved and you can easily apply to other post-processing results as well. So this is the result file that has been generated. It's a smooth animation of our simulation result. Of course, we could still adapt our isometric levels, but just for showing what happens, this is a pretty good animation at that point. So if there are any questions, just write us info@SIMetris.de or support@SIMetris.de. We're ready to answer your questions. Thanks for watching. Goodbye.